Hello to you from ChemHelp ASAP. In this video, we will show the acetylation of a molecule called benzoin. We will discuss the reaction, perform the experiment, isolate the crude product, and perform characterization of the isolated product. Handouts for the lab procedure and NMR spectra are available through links in the video description. To start, I would like to briefly define an acyl group. In organic chemistry, everyone gets comfortable with alkyl groups pretty quickly. Methyl, ethyl, propyl, etc. These are carbon groups that are attached to a molecule through an sp3 hybridized carbon. Students also encounter acyl groups, but they appear late in courses and I don't feel students get as comfortable with them. So, acyl groups are carbon groups that are attached to a molecule through a carbonyl group. To the right, we have three different acyl groups. The smallest acyl group is a formyl group. It has just one carbon, the carbonyl carbon, and is capped by a hydrogen. The next acyl group has two carbons. It is an acetyl group. Acyl and acetyl sound very similar, but they are different. Acyl refers to an entire type of group. Acetyl is a specific example of an acyl group. Our reaction today involves addition of an acetyl group. Of course, you can't have more carbons. The last acyl group listed is the propionyl group with 3 carbons. Okay, let's move on to some acylation chemistry. The reaction in this video is an acylation, and I think most instructors present acylation reactions in one of two ways. The first is on top of the slide. Acylations are often first encountered in a unit on acid derivatives, and acylations are presented as a transformation or interconversion of one acid derivative into another acid derivative. For example, in the top reaction, one acid derivative, often an anhydride or an acid chloride, reacts with a nucleophile, here an alcohol, to form a new acid derivative. In this case, we make an ester. Thinking of the reaction in this manner focuses on the acid derivative carbonyl carbon. The carbonyl starts as part of an acid derivative and finishes as part of an acid derivative. The alcohol nucleophile is almost an afterthought. On the bottom of the slide is another way to think about this reaction. Now we are putting the alcohol on the left. The alcohol is the featured starting material. The alcohol reacts with an acid derivative, again, often an acid anhydride or an acid chloride. The acyl group is transferred from the anhydride or acid chloride to the oxygen of the alcohol to form an ester. In the ester, here is the new acyl group. The lower reaction treats the reaction the same reaction as the top line as an acyl transfer reaction. While acylations are normally first encountered as shown in the top line, in the literature, I'd say most acylations are written as shown in the bottom line. Normally the nucleophile, an alcohol here, is the main molecule of interest and given the premium position as the main starting material. Our reaction today follows the lower model. How the reaction is portrayed ultimately depends on which molecules are being highlighted in the synthesis. Finally, we are ready to talk about our reaction. We are reacting benzoin, which contains an alcohol as a weak nucleophile with an acylation reagent, acetic anhydride. Here is the full structure of acetic anhydride. When acetic anhydride reacts with a nucleophile, it transfers an acyl group, specifically an acetyl group. The product is called benzoin acetate. These acylations can be performed under either acidic or basic conditions, depending on the specific transformation. Under basic conditions, you might first deprotonate the alcohol to make the oxygen more nucleophilic. Under acidic conditions, you might protonate the carbonyl of acetic anhydride to make it a strong electrophile and therefore more likely to be attacked by the alcohol oxygen. This exact reaction is well known in the chemical literature. I'm approximately following the procedure described in the reference at the bottom of the slide. Great, let's do this reaction. Well, we have just one reagent to weigh out for this reaction, and that is benzoin. I'm going to show you this bottle. Oh boy, this is, I don't want to hold it that way. This is benzoin. This is one old bottle. I'm not sure how old it is, but again, just because a reagent's old, a lot of these reagents stored just fine. So that's not a problem. So I want to get out of here about 1.06 grams. So the molecular weight of benzoin is 212 grams per mole. And I want 5 millimoles, and that's going to be 5 times 212 in milligrams. And that's 1,060 milligrams. Okay. There we go. Okay, it's starting to come out now. Good. Okay, there's a tenth of a gram. 0.3. And as I say, almost every one of these videos, I don't need an exact precise amount to be weighed out, but I do want to know exactly what I get. So that's 1.03, 1.045, oh there we go, 1.062. Okay, I'm going to call that 1.06. So that is very close to exactly 5 millimoles of benzoin. And now we're ready to go to the hood. Well, here we are in the hood, and this is going to be our reaction flask that is a 20 milliliter acetylation vial. And you might notice something. You might notice that I am wearing gloves. I confess, I'm, as far as most chemists go, I'm a little bit older, and I learned chemistry at a time where fewer people wore gloves. And I find that gloves make me somewhat clumsy, and so I tend not to wear them. But there's a reagent we're going to work with in this experiment that I will wear gloves for. So gloves are a protection, and there are times when you absolutely need protection. There's no argument against it. Note that you might watch these videos and say to your instructor, well, the dude on Chem Help ASAP doesn't always wear gloves. If your instructor wants you to wear gloves, wear gloves. That is not a fight that's worth fighting. Just follow the protocols that the people in authority over you have put into place. So, you know, don't... Yes, these videos are examples of how to do chemistry, but ultimately you are... I'm not assigning grades. I'm not doing that kind of thing. Just when someone says, wear the gloves or do this, you just say, yes, sir, yes, ma'am, and go on your way. Okay, so this is our reaction flask, this innocent 20 milliliter acetylation vial, and it has a stir bar in it, small stir bar. And I'm going to transfer our 1.06 grams of material. I'm not going to put that on. This hot plate is warm because I want the reaction to be hot as soon as we get it going. But I don't want to put our dry material on a hot plate. So we're going to add some things to this. We are going to add 1 milliliter of acetic anhydride, and I have a pipette off camera, and I'm going to squirt in a milliliter of acetic anhydride. Wonderful. And let's change out tips. And now we're going to add a milliliter of acetic acid. That's great. Now this is not just acetic acid. This isn't just vinegar you find at a grocery store. This is glacial acetic acid. Glacial acetic acid is pretty strong stuff. But the strong stuff that really is notable is sulfuric acid. And I have a big bottle of it. Sulfuric acid. Sulfuric acid is tough stuff. And sulfuric acid comes in multiple grades. This is 98% sulfuric acid, which is mostly what you find. Sulfuric acid is exceptionally reactive. If you get a drop on your skin, you will immediately feel the burn. And that I think that burn is really because it's exothermically breaking down the fats in your skin. It is tough stuff, and because it's so thick, it doesn't rinse off as quickly. So it's got a little it's got a little holding power on your skin. And of course, I don't want to talk about what it'll do to your eyes. It's incredibly destructive stuff. So I have just a little bit to make it easier to handle, a little bit of sulfuric acid, and I want to get 5 drops. And no, because it is thick, it doesn't pipette as easily. It's very viscous, very slow to be drawn up in this pipette. Now I'm not going to be super precise on this, and tell you what, let's I'm going to hold that right there. Get this stirring a little bit. Now we're going to add in our sulfuric acid, and we're going to get these little tiny drops. I'm not going to count those. That's 1, 2, 3, 4, 5. Okay. So maybe we got a little more than 5 drops. That's okay. It's actually catalytic and acid. Okay, now this is going. We can see it's kind of yellowed. And as it stirs, according to the procedure we're following, the acid helps dissolve the benzoin. Also, this is getting warmer, so the heat is probably helping as well. Now, we're going to let this stir. And if you notice, on this side where I put in the solid, I got a little solid on the side. So I am going to see if I can't rinse that down in. And again, this is not nearly as reactive as pure sulfuric acid. The sulfuric acid has now been diluted into acetic anhydride and a glacial acetic acid. But this is a pretty acidic mixture. So anytime you're in lab and you're working with super strong acids or super strong bases for that matter, always be careful. By all means, do wear gloves. Also notice that acid solutions tend to look like water, just like strong base solutions look like water. So it's easy to see droplets of liquid on the benchtop and assume that it's water because it looks like water. But in the end, you find out it's not water. And one of the great casualties of acids and bases in lab will be your clothing, because you'll reach across the benchtop and drag your sleeve, or maybe rub against the bench with your pants, and you'll find there was something wet there that wasn't water, it was acid. And then when your clothes go through the washing machine, you've got holes in your clothes. So just be mindful. You don't have to be fearful of chemicals, but you certainly have to respect them and what they can do, and take precautions to prevent that from happening. Okay, so this is stirring. Everything's in solution. We're going to give this 20 minutes, and then we're going to come back and see what it looks like. Well, it is 20 minutes later, and this is stirring. Really, the appearance is unchanged. Now, according to the procedure, this reaction is supposed to heat on a steam bath. So this is from an older reference. And steam baths were a very common way that people would heat things, 75 years ago. So now I'm using a hot plate. I set the hot plate to 100 because that's about where steam is. But the procedure is very explicit. Don't heat it for longer than 20 minutes, and don't heat it excessively. Don't heat it a lot more than you get off a steam bath. So really, this reaction's run its course. However, I don't want to continue on with this reaction because I really have no visual evidence that anything has happened. I just know the procedure said to go 20 minutes. And a lot of reactions, if you just go based on the time in the reported procedure, it may or may not be complete. Now, I do a lot of reactions on the channel, and a lot of these, the reaction forms a precipitate. And so there's a visual indication it's done. But we have nothing for this reaction. So I'm going to go ahead and I'm going to take a TLC of this reaction. And if you notice in the bottom right, we have two tiny test tubes. This is a test tube with a little bit of ether in it and a little bit of our starting material, benzoin. So I have authentic starting material that I can compare to the reaction. And of course, we have whatever's in the reaction mixture. So I'm going to compare the reaction mixture to this authentic starter material in a 3-lane TLC plate. But I need to do one thing for our reaction. So our reaction is full of acids and acetic. It's full of all kinds of stuff. So I want to get that away from the reaction. What I'm going to do is something called a mini workup. So here is an empty, tiny test tube. I love these tiny test tubes. I'm going to put just a little bit of water in here. It takes very little. That's plenty, maybe more than I intended, but that's fine. So now we have water in here, and now, off camera, I'm going to get a little bit of ether. And I'm going to squirt some ether in here, probably drip it everywhere. That happens with ether sometimes. And now you can see that there is, maybe you can or can't see, there is a bottom layer. I'll try to hold it closer. There's a bottom layer that's water, more dense water, and the top layer is ether. I'm going to take a drop of our reaction mixture and put it in here and give it a chance to mix, and then our product should go into the ether layer, and all the acids and really polar materials ought to stay down here. And now when I do the TLC, I'll just sample from the ether layer. And this is, we're really doing a miniature aqueous extraction of this reaction. And we're just taking a little sample. I'll just get a drop. Takes maybe not in a full drop, maybe more than a full drop, I don't know. Okay, so that dropped down. I don't know if you saw it sink. I'm now going to use this pipette. I'm going to suck up this whole thing. Got to be a little careful when you do this, because it's easier to squirt too vigorously in your test tube and just shoot everything all over the place. But I'm just drawing this up, squirting it back down, and I'm using this to generate a mixing action, so that everything gets all mixed up. So hopefully what's done is our product is up top and all the residual acids and polar materials are down in the bottom. And now I'll sample this from the top layer. Whoops, I got a spare. I don't need that anymore. And here's our starter material, and I'll use these two samples as the basis for a 3-lane TLC plate. Let me come right back in. Note the procedure did say don't heat this too long. So while I'm running the TLC plate, because the TLC plate might take you 10 or 15 minutes, I'm going to take this off the heat and just let it come down to room temperature. Because in case this is already complete, I don't want to be cooking and potentially destroying any product while I'm trying to get the information to determine whether the reaction is complete. So we'll take that off the heat while we're performing this TLC. Here is our 3-lane TLC plate. It was developed with a mobile phase of 20% ethyl acetate and 80% hexane. Note that the leftmost lane is the starting material alone. The rightmost lane is the reaction mixture from the mini workup. The middle lane is a co-spot, both the starting material and the reaction mixture. What do we see? Well, the starting material has one spot, just starting material. Perfect. The right lane has a new dark spot that should be product. There is another faint spot a bit higher up on the plate. Note that the reaction lane does not have any starting material spot. That's good news. That means that the reaction has completely consumed the starter material. This reaction is indeed complete after 20 minutes of heating. So for thoroughness, let's list our RF values. The starter material has an RF of 0.26. The likely product has an RF of 0.32. And the impurity has an RF of 0.44. This is a nice result, but we do possibly have a side product, the higher spot. We'll need to look out for this impurity at the end of the reaction. Well, that TLC looked great, so let's go ahead and continue. For the next step of the reaction, it calls for addition of our reaction mixture to water, a volume of water. That's about 12.5 milliliters of water. Now, if you'll notice, I've got a little red light on the hot plate. So I've turned off the hot plate, but that means the hot plate is still a little bit warm. I mean, it could actually still be very hot, but it's not very hot. But it is warm. As we add this mixture, eventually we're going to get precipitation in this flask. And actually, precipitating from a warmer solution is sometimes a little bit more advantageous than just keeping things as cold as possible. So I'm not going to worry about that little bit of heat. Okay, so we have to transfer this. The procedure calls for a fairly slow addition. I'm not going to do a super slow addition, but we will go dropwise with this solution. I do want this to be stirring pretty efficiently. Okay, there's a drop. Let's see it going in. Nice efficient mixing. I think that's given us some solid. It's hard to tell if it's solid or an oil. I think that's solid. I will confess, I've done this reaction before. I didn't record it. And I did have trouble at this stage. I actually got quite a bit of oil out of the reaction. And it took a little work getting that oil to solidify. So I'm a little bit gun shy here about getting a solid. And the procedure does warn you about making sure things are vigorous and moving well. Typically in the precipitation, if you can get some solid, you're probably a-okay to continue. Now I'm not sure that's a solid. I think that's maybe oiling out on the stir bar. In which case, well, we're just going to have to try to fix it. Okay, let me draw up the solution again. That's definitely oiled out. Only an oil would be that sticky and eventually aggregate on something like the stir bar. And you'll see that this is getting cloudy. When you form solids, unless they're super fine solids, they don't look cloudy. It looks like you have solid floating in a clear solution. This does not look like a clear solution. This looks like a cloudy, almost like milk. Much more of an emulsion. But that's okay. I think I can fix that. Okay, so we're still adding with good vigorous stirring. And there's one pipette. Let's go for a second pipette. Oh, the cloudiness. That's okay. You know, one thing I'll say, it's nice to see the reaction behave consistently. If it happened to me in the previous reaction, it's at least reproducible. And of course, if it's reproducible, then I have more confidence that the way I fixed it last time, we'll fix it this next time. Okay, we're almost there. Now the way I'm transferring this, we're going to lose a little bit of residue in here. Yeah, that's just the brakes. There's always a cost in doing transfers. I'm not going to try to add water in here and transfer it over. We're just going to leave that as is. I mean, that's, you know, we got 99.5% of it. I think that's adequate for what we're doing. Okay, so I'm going to let this stir, and I'm also going to make preparations for my backup plan. And we'll come back on camera. Maybe we'll let this stir for 5 minutes and make sure it's not going to solidify. And if I hadn't done anything in 5 minutes, I'll come back and we'll do something else. Well, within no time, this actually solidified. I'd say it took maybe less than, I don't know, 1 or 2 minutes. So we'll let that stirring stop. Now, I'm not sure if that's apparent. Get my hand out from behind. That's a solution that's clear, that has solids suspended in it. You know, that's not what it looks like to look through a glass of milk. That's definitely solids and a clear solution, and that is what we're looking for. So now if you notice, shouldn't have gotten this stirred up again, there are some pieces towards the bottom, and I don't like those large chunks. The problem with large chunks in a precipitation is that you start to get aggregations that entrap impurities. So I'm going to go in with a spatula and I'm going to smash that up a little bit. But ultimately the next step is going to be we're going to filter off the solid. But first I'm going to break up those solids, and I'll go ahead and do that off camera because that can be a little bit tedious. But there's nothing fancy to it. I'm just going to take a micro spatula and go in and try to trap the larger solid pieces against the side of the flask and smash them up. So that is just brute force work. So I'll be back in a couple minutes. Okay, we are ready just to do a filtration. There's nothing fancy about this. We have a Buchner funnel, we have a sidearm flask, and we're attached to the vacuum line. This solution is essentially water, so I'm going to seat our filter paper with water. Looks good. I'm going to peek inside the funnel and make sure all the holes are covered up. Yes, they are. Looks fantastic. And now we're going to take this and just dump it in. Now, I did allow the stir bar to go in as well. I did that because that stir bar does have a little solid adhering to it. You can see there are some chunks, so I tried to break it up, but clearly I didn't smash it up into powder. I mean, it's hard to do when you're in the bottom of a little acetylation vial. So that's okay. We'll swirl this up, get that in. Now that's starting to look a little bit of transferred. Let's try one more of those. Great. Tell you what, we might try a couple more of those, because there is, in that original solution, there's a fair amount of acetic acid, and we want to try to make sure we rinse off everything that we can. There's more water. That might fill up a receiver flask. That might be enough. Okay, I think that's a good enough rinse. That is done. Let's take a little peek inside the funnel. There's our stir bar. There's our solid. And hopefully that's a pretty good recovery of material. So the next step will be to take this material, to put it on, spread it out on a watch glass and let it air dry. Then we'll get a mass and we'll start to collect some characterization data. Well, our product is nice and dry a day later. Here it is. That's a net mass of 1.22 grams. It's 1.22 grams of what is presumably the benzoin acetate. So let's go ahead, and that's our recovered mass. So ultimately we'll need to calculate a yield on that. But for now, let's go ahead and make sure that this is fairly high purity material. Okay, let's first look at the TLC plate. I know that we've taken a TLC before, but that was a 3-lane TLC plate to determine whether the reaction was complete. We are now performing a TLC to determine how pure the product is. I did spot 3 different amounts of product on this plate, but all 3 of these spots are the same, the crude isolated product. We are pretty much just one spot on this plate. If there are more spots, they are faint. The good news is we don't see the impurity that we saw before. That's nice. Like the previous plate, this was performed in 20% ethyl acetate, 80% hexane. The RF of the spot is 0.31, certainly within error of the previous product RF of 0.32. How about the melting range? The melting range was 78.5 to 79.8 degrees Celsius. This is a nice sharp melting range, but it's a bit lower than the literature melting point of 80 to 82 degrees Celsius. That's not a huge difference, but it's a bit low. The literature value is taken from the same reference shown on the earlier reaction slide. Overall, the TLC and melting point look pretty good. How about the NMR? Here is the full NMR spectrum. This spectrum was performed at 400 megahertz in deuterated DMSO as a solvent. Let's first zoom into the downfield region, and then we'll look at the upfield region. The first peak I want to discuss is the singlet at 7.1 ppm. This hydrogen is the one next to the carbonyl. This chemical shift might be surprising. Normally I look for alkyl hydrogens to be in the 1 to 4 ppm range, but this one is at 7.1. Why is this so far downfield? Well, the hydrogen is next to an oxygen. It's also next to an aromatic ring. It's also next to a carbonyl. All those factors collectively push the signal way downfield, all the way to the aromatic region. The other downfield signals are not nearly so interesting. This 2H doublet at about 8 ppm is likely from these two ortho hydrogens. The carbonyl is an electron withdrawing group and deshielding those hydrogens. This triplet at 7.6 ppm is likely the parahydrogen on the same ring. The signal around 7.5 ppm is a multiplet with 4 hydrogens. If you look closely, it looks like a doublet right next to a triplet. The triplet is probably buried under there a little bit. The doublet would be from the ortho hydrogens on the other ring, and the triplet would be the meta hydrogens on the first ring. The 3 hydrogens at 7.4, again a multiplet, are just the remaining meta and para hydrogens on the other ring. Now here is the upfield region. We have 3 signals. 2 of these are from the NMR solvent. We have water around 3.4 ppm. We have DMSO at 2.5 ppm. That leaves this 3 hydrogen singlet at 2.2 ppm. That is our methyl group from the acetyl group. Overall, this spectrum looks great. The baseline is pretty clean. Despite being a crude product, this seems to be clean material. All the characterization data look good. Let's finish things up by calculating the yield. Our 2 reagents are benzoin and acetic anhydride. We used 1.06 grams of benzoin with a molecular weight of 212 grams per mole. That comes out to 5.0 millimoles of benzoin. Acetic anhydride will take a bit more work. We used 1 milliliter of that reagent. The density of acetic anhydride is 1.08 grams per milliliter. So we used 1.08 grams of acetic anhydride. The molecular weight is 102 grams per mole for a total of 10.6 millimoles. These 2 reagents react in a 1:1 ratio, so we have far less benzoin. Benzoin is the limiting reagent, so the theoretical yield is 5 millimoles. Now for our product. We obtained 1.22 grams. The molecular weight is 254 grams per mole. That's 4.80 millimoles. This is our actual yield. For percent yield, take actual over theoretical times 100. That's a 96% yield. Great. The literature yield is also exceptionally high, close to 90%. This is an excellent high-yielding reaction that affords a very clean product. I hope you enjoyed this example of an acylation reaction with benzoin acetate as the product. If you are interested, handouts for the procedure and copies of the NMR spectra are linked through the video description. As always, please subscribe, like, or leave a comment. Take care.